So last Monday, we looked at the idea of diffraction, okay, and we saw that diffraction and reflection are quite similar in the sense where reflection, okay, are quite similar in a sense where there is an obstacle, okay, but something else that differentiates diffraction, okay, from reflection is the existence of a small gap or a slit. Okay, slit gap is the same thing. Okay, and we saw that there are two kinds of diffraction patterns. Either a circular pattern, okay, or what is the other one? What is this called? How is this pattern described? Anybody? Can you describe this pattern for me?
Plain and bend at the edge.
Okay, it's plain and bend at the edge. And so we call this kind of diffraction, okay, a less obvious diffraction, macam dia tidak terlalu tersebar, okay, because there is a wide gap. Okay, whereas a circular one, a circular diffraction, okay, shows a more obvious diffraction pattern. Okay, especially when we're talking about water waves. Okay, and so we find that there are two conditions that are very important in order for the diffraction to be very obvious. Number one, your gap must be small. And number two, your wavelength must be long enough. Okay, and I would like to add one other thing here. This small gap, can you make a star over here? And you write, the small gap, the size must be smaller than the wavelength. Okay, if the gap is if the gap is small, okay, small also must compare with something smaller, kan? So usually we say if the gap is smaller than the wavelength, okay, then the diffraction will be very obvious. Okay, so this is also an important condition. But basically, we want a small gap and we want a big wavelength. Okay, so that the diffraction pattern will be a circular one and definitely a more obvious one. Oh. Okay, a more obvious pattern. Okay, so that's water waves. Today we're going to look first at sound waves. Okay, so we have audible sound waves that have a range of 1.5 to 15 meters wavelength. Okay, so sound waves have different wavelength depending on the frequency. Okay, but it can be as short as 1.5 cm or as long as 15 meters. 15 meter wavelength is a pretty long wavelength. Okay, and so light waves have a range of 4 to 7 times 10 to the power of -7. It's very, 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 very tiny wavelength. Okay, but we talk about sound first. So a radio is placed in the nearby corner of the wall. Okay, the radio is then turned on. Okay, first of all, take a look at these two pieces of information. Okay, and let's compare. Compare the wavelengths between the sound waves and the light waves.
The wavelength of sound waves is bigger than the wavelength of light waves.
Okay, this is the first and quite an important fact for us to remember today. Okay, the wavelength of sound is so much bigger than the wavelength of light. Okay, and this will become very important later in the second half of this class. The first thing we need to remember is this. Sound waves have very big wavelengths, okay, compared to light wave. Okay, cm only, paling kecil pun 1.5 cm, and paling besar is 15 meters. Now remember the condition I said just now. For a diffraction to be very obvious, you have a bigger wavelength is much better. Okay, this is the foundation for everything that we're studying today. Big wavelength is always good, very easy to diffract. Okay, and so this is a very important thing you need to remember. Okay, so let's say you're a guy standing here. Okay, can you see the radio? Obviously you can't see the radio, but you can hear the sound. Okay, I think there's a video here, but let me see. Let me see the video. Oh, okay.
Saja dapat mendengar bunyi radio di belakang dinding, walaupun tidak dapat dilihat. Ini menunjukkan gelombang bunyi dibelaukan.
Sorry, could you hear this one just now?
Yes.
Can hear the video. Can
hear.
Okay, sorry. So, this student, okay, could hear the sound from the radio, although he could not see the radio. And this happens to us every day. And we don't see somebody, but we can hear somebody talking. Obviously, we know that person exists, although we can't see the person. And this is because, okay, um, we cannot see the radio because light is very difficult to refract. Okay, if we can see, okay, not obviously also because it's hidden behind the wall lah. But one of the things that we need to remember is because since light waves, the wavelengths are so small, light is very difficult to be refracted. Okay, that is the inference that we can make about the diffraction of light waves. We'll talk about light waves in a little while lah. Okay, but sound waves, can you hear the sound of the radio? You can't see. Therefore, light wave is very difficult to diffract. But you can hear the sound of the radio. And therefore, okay, sound waves can easily be refracted. Oh dear, easily. Okay, sound waves can easily be refracted. And they are easily refracted because...
Saya dapat mendengar bunyi
Okay,
radio
thank
di
you.
belakang dinding.
Okay, they're easily refracted because the sound wavelength is so much bigger than the wavelength of light. Okay, so it's very easily diffracted. The energy is very easy to spread out. Okay, because we can hear it. Because the wavelength is long enough, is big enough, it's so big. Okay, that it's so easy to diffract. Remember the two conditions for diffraction obvious: small gap, small wavelength, small slit, or big wavelength. Okay, and in this case, we're not so concerned about the gap or the obstacle. We're more concerned about the wavelength. Okay, compared to light waves, sound waves have a much bigger wavelength, and so it's much easier to refract. At night, when somebody is singing karaoke very loudly, right? You don't need to see, you can hear one. Okay, and the reason why we can hear is of two reasons. Number one, there is refraction that is happening. We saw this in refraction. But number two, the fact that sound waves have a very big wavelength is very easy to spread out. Very easy to spread out and very easy for everyone to hear. So the lesson behind this is if you want to sing karaoke at night you got to make sure that your voice is nice lah. Otherwise, people are going to start to complain about your noise. If you don't want people to complain about your noise, then you do karaoke in the daytime. Because karaoke in the daytime is a little bit hard to hear, okay, because less refraction, okay. But nevertheless, diffraction happens better and easier with sound waves, okay, compared to light waves because of the difference in the wavelength. Okay, the wavelength is a very big and important factor. All right. So in this second one, okay, I'm going to ask you to do the simulation again, okay, but I would like you to take a screenshot of these two questions. There are two extra questions that I also want you to answer. Okay, you are about to see a simulation where there is a laser pen that gives out different colors, and we're going to pass it through a single narrow slit and a small pinhole. Pinhole is like this lah. Okay, and we want to see the pattern that comes out. Okay, so two extra questions besides the one in your module. So the one in your module is page 150, activity 4. Okay, so do all the questions in page 150, activity 4, plus these two questions. Okay, jot down and tell me which color has the biggest and the smallest wavelength. Okay, and secondly, which color gives a more obvious diffraction pattern. More obvious pattern means what you will see is it is more separated lah. Okay, I will show you in a little while. Okay, which color gives out the most obvious diffraction pattern and which color gives out the least obvious diffraction pattern. Okay, and so I'm going to show you, I hope you have copied this. So again, when you come here, the other day we did this, right, slits. Okay, today we're going to do proper light diffraction. Okay, so you click on this. Now, when you click on this, you're going to see a few things lah. Okay, number one, you're going to see different colors. Okay, I want you to explore all the colors that are, but if you can, just explore the basic the seven colors of the rainbow. Okay, starting from red and last one is purple lah. Sorry, indigo, ungu. Yeah, okay. So you can explore all the seven colors, and you will notice that different colors have different wavelengths. Okay, you have to answer the question over there. Now, I'm just going to use yellow color as an example. This is right in the middle lah. Okay. Now, what you do is, this is the slit. Okay, so this is the click for the slit. Don't need, if you want to do this, you can do this after lah. Okay, up to you if you want. But the first one is a slit. So this is a slit. I suggest that you set the width to as small as possible, because if you have a bigger width now, you know what happens. Okay, what happens if the width is very big? Diffraction pattern is not going to be obvious now. Okay, so you set the width to the smallest. For the purpose of our activity first lah, finish the activity, then if you still got time, then you can play around with this simulation. But for the purpose of our activity, set the slit to as small as you can, okay? And then the height, you just leave it somewhere in the center. It's totally fine like this. Okay, and then you turn it on, and this is what you will see. Okay, now this is what I mean. A diffraction pattern for light as it passes through a slit, okay, will be kind of separated lah. Okay, you can see the separation. So the more obvious the separation, the more obvious the diffraction. Okay, I repeat, the more obvious the separation between the yellow, because you see yellow, black, yellow, black, yellow, black. So the more obvious the separation, okay, the more obvious the diffraction, means it is diffracted more lah. Okay, if you find that it's very difficult to see the separation between the first yellow and the second yellow and the next yellow, then the diffraction is not very obvious. So you need to tell me, one of the questions I asked just now, right? Which color has the most obvious diffraction pattern? Which color has the least? So you need to, do this simulation in order to find out lah. So this is the slit, okay, over here, and this is the pinhole. So when you click on the pinhole, you will see something like this lah. Okay, again, set the diameter to as small as you can. Oh, hold on. Yeah, okay, fine. Set the diameter to as small as you can, but if you don't want, you can always set it to somewhere in the middle like this. It's fine. But the eccentricity, this one, okay, set it to here. Don't go all the way here, because this is very weird, very difficult to draw. Okay, look at the eccentricity, okay. So let's set it to the minimum eccentricity, but you can change the diameter if you want, depending on how rajin you are to this one. Okay, but what I need you to discover, okay, is there's a difference between the slit pattern and the pinhole pattern. Okay, and again, I will ask you the same question lah. Okay, which one is a more obvious diffraction pattern? Which color? Okay, and which one is the least obvious diffraction pattern? Okay, so now it's 10:20. I'm going to give you 15 minutes to complete this. Okay, I'm posting up the link in the chat now. So when we come back at 10:35, I hope that everybody is ready to answer the questions that are in the activity. Okay, 15 minutes from now. Let's take a look at this. So obviously the diffraction pattern can be seen lah. Okay, can be seen. So let's start with the slit lah. Okay, I think if we start with just the red color, okay, so we will see that the diffraction pattern is kind of like this lah. Okay, there is going to be red in the middle, okay, and it's pretty bright. Okay, and then after that, there's going to be this one. Actually, you know what? Let me not share this. Let me share the other one. I think this is a more proper one. Okay. Sorry. So, sorry. Hold on. Okay, so if it is a small slit now, okay, actually you will see that this one lah. Okay, there's black, red, black, red, black, red, black, red. I'm just using all black over here lah. Sorry, all red over here lah. Okay, so obviously the difficult part is how do you describe the diffraction pattern, because this is not circular. This is not water wave, so we can't say it's circular, and we can't say that it's plain and bent at the side because it's not water wave mah. Okay, so how would we describe this? This would be how it would be. It would be black and bright lines alternately. Okay, be alternating black and white bright lines. Okay, and it will be brighter in the middle. We find that in the middle is where it is most bright. Okay, so this is how we would describe the diffraction pattern for light waves. Okay, for light waves. So I hope that you can draw the diffraction pattern. Okay, basically, if it is a pinhole, it's just circle, circle. If it is a slit, then it's just black, red, black, red, black, red, black, red lah. Okay, so question number 3. What is the difference in the image formed by the angle of a single wide slit, okay, and a single narrow slit? Anybody want to try? What is the difference between the two? When you did a simulation, when you did wide slit, narrow slit, what is the difference that you can see?
The frequency, I don't know the frequency. The amount of lines lah. The
The amount of lines. I think that's a good try. Okay, obviously, I think what Ethan is trying to drive at, okay, and if I'm hearing you correctly, I think that is a very big difference. There is the amount of lines, okay, and there are more lines when you use a wider slit. If you use a smaller slit, you find that the red in the middle is very panjang. Kan? If you use a wider slit, you find that the red in the middle is very pendek, but there are more reds that you can see. No? Do you notice that when you were doing a simulation? If you use a small slit, the red in the middle is very big. But if you use a wider slit, the red in the middle actually becomes very small. In this picture, it's not really doing it justice, but actually this is zoomed in already. This one is zoomed in. But actually you see that the red in the middle is very tiny. Compared to if it is a small slit, the red in the middle is very, very big. Okay. And so how I would describe this, okay, would be like this lah. So if it is a wide slit, okay, you will have a very bright light in the middle, okay, but the dark and the bright lines are not very obvious, okay, as compared to a small slit. A small slit, you'll find that the dark and the bright lines are alternate. Yes, it is brighter in the middle, not as bright as this one. Okay, because remember what happens after diffraction? After diffraction, the wave spreads out, and the wave spreads out. So if the wave spreads out by right lah, okay, it shouldn't be very bright in the middle. Okay, the very fact that it is very bright in the middle, if you use a very big slit, okay, means that the diffraction is less. Okay, let me show you the tab again. In this one, in our simulation over here, it's unfortunately not very obvious lah. Okay, but you will find that when you use a narrow slit, okay, it is you see as compared to this, right? So you can't really see the difference in the brightness. All we see is just the difference, the difference in the number of lines lah. Okay, so we know that the bigger the width, the less obvious the diffraction pattern. Okay, so you cannot really, it is this one, the red and the black lines are not as obvious as compared to if you see this one. Very clearly you can see the red, you can see the black. There is a very distinct separation between them. Okay, to show that it is the diffraction pattern is much more obvious over here. Okay, compared to this. So let me repeat this once again. So if it is a wide slit, okay, okay, it is bright in the middle, but the diffraction pattern is less obvious. Okay, if it is a narrow slit, kalau dia punya slit kecil bahkan, number one, it is bright in the middle, but the diffraction pattern is more obvious. The dark and the bright lines are more clearly seen. Okay, let me repeat. The narrow slit is more important. The dark and the bright lines are more clearly seen. Okay, compared to the wide slit. So again, for the slit, okay, for the one in the wide slit, okay, the light in the center is very bright. Okay, the light in the center is very bright and very obvious because remember, big slit means less diffraction. Less diffraction means the energy is not spread out so much. So most of the energy is still centered in the center, in the middle. But in a small slit, the energy is spread out much better. So yes, although it is bright in the middle, but it is not as bright as the one with the big slit. And the distinction between the black and the green lines or the black and the red lines is much, much more obvious in a smaller slit than a bigger slit. So the diffraction pattern in the smaller slit is much, much more obvious. Okay. Now, in the pinhole, it is the same thing. What happens to the light as it passes through the pinhole? It will be diffracted, but the diffraction pattern is different. Okay, since it is a hole that we're going through, okay, so the diffraction pattern will be red, black, red, black, red, black, and this one. Okay, now let's come back to the question that I asked earlier. Okay, and I think you can answer this. Which color has the biggest wavelength and which color has the smallest wavelength? Anybody?
The smallest is purple, the biggest is maroon, red, maroon, something like that.
Red. Hello, colors of the rainbow, red. Okay, so the smallest is purple and the biggest is red. Now remember, diffraction is very obvious when the wavelength is bigger. The bigger the wavelength, the better the refraction will be. So which color will give a more obvious diffraction pattern? And I hope that using the simulation just now, you would have seen that. Which color? Which color is more obvious?
Red.
Okay, and which color is least obvious?
The purple one.
Purple one lah. Okay, the purple one is the least obvious because least obvious because it has the smaller wavelength. Okay, now again, remember the reason why diffraction in light is very difficult to see because the wavelength, even though red is the biggest wavelength, right, it is still 10 times 10 to the power of -7, It's still very, very, very small. Okay, so your slit, remember just now I said the size of the gap must be smaller than the wavelength. So this is a very difficult experiment to do at home because already the wavelength of light is so small, then your slit must be even smaller than the wavelength so that the diffraction can be seen. Okay, which is why, okay, in diffraction for light especially, we will usually do it using like super canggih method okay, which is what they did in this video. Okay, so take a look. I don't think there's any sound here, but okay, so you can see MIT is a famous place, Department of Physics. So they see a single slit diffraction shining a laser through a small slit. So this is a red laser. Obviously, we don't have this in the mount. This is a slit. Okay, variable width. You can change the width, but it's just one slit. Okay, so light passes through. They turn off the light. Of course, from far away, it looks like very blurred, right? Okay, one single light now can become one whole long spectrum. But when you change it now, you see that the diffraction pattern becomes more obvious. Okay, you're making it wider. Okay, you're making it wider. So let me zoom in. Okay. So you're making it wider. When the slit width is increasing, notice that the light in the middle becomes bigger. The light in the middle becomes brighter because there's less diffraction. Okay, the wave is not being spread out, it's just going straight through. Okay, so most of the light is not being diffracted. That's why the center is very bright. Okay, and you find that the dark and the red lines become less and less obvious. You can't really see the difference much, as opposed to when this was beginning. See, the beginning over here. Okay, so you see this one, the red and the black is more obvious. So small slit. Okay, so this is a pattern of a small slit. And as the slit is increasing, getting bigger and bigger, the diffraction pattern becomes less obvious and the light in the center becomes more bright. Okay, because there's less diffraction that is happening. Okay, now they are decreasing the width the slit width. Okay, so you can see. All right, I think the next one is pinhole. Okay, shining a laser through a pinhole. So yellow laser, and then they're going to use yellow for some reason, and then pinhole over here. Pinhole is just a pinhole. Okay, you poke a hole using a pin. So yeah, so when the diffraction happens, let's zoom in and take a look at this one. Zoom, 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 zoom. Okay, and this is what you will see. And the reason for this, the reason why it's not so circular, partly because number one, they're using yellow. They're not using red. Red will be a nicer one, but they're using yellow in this instance. Okay, and so you will get this one. And I think also partly because why this one, because the pin is not really circular. Okay, you get this like kind of weird looking pattern over here. Okay, so again, okay, just to remind you that different colors have different wavelengths, which we will talk about this in the end of this chapter. Different colors have different wavelengths, and we have seen that actually red color compared to purple color gives a more obvious diffraction pattern. Okay, more obvious means the center is not so bright. Okay, remember, because this energy is all spread out already. So the more spread out your energy is, okay, the less bright your center will be. The brighter your center, the less diffraction that has happened, because the light just goes straight through saja. Okay, and so that is the thing lah. All right. Now let's end by looking at a few examples. So this is the water wave. Okay, so usually at the shore or at the someplace where there's dizziness, okay, you will put a barrier over here. Okay, you put a barrier over here so that when the waves come in this fashion, okay, they are going to be diffracted. Okay, and it can be very big because we don't have to worry about the water waves. Water waves generally the wavelength is pretty big lah. Okay, but the slit is small enough. Okay, so that it can be done. So compare the amplitude of the sea wave before and after passing through the wall opening. What do you think happens to the amplitude after it passes through this wall? What do you think?
Decreases.
Okay, the amplitude will decrease. Why? Because remember, okay, the energy has lessened. After diffraction happens, energy is less, which is good, okay, which is good for all these ships over here, because we don't want all the ships to always terhumbang-hambing when they are parked there, otherwise we need. So by relating the size of the wave with the energy, explain how the erosion effect, okay. So let's talk about erosion effect. So we build barriers with small openings, okay, so that diffraction can occur. Okay, and when diffraction occurs, the energy of the wave is spread out into a larger area. So you don't have all the waves coming to you at the same time. Okay, it will be spread out, okay, and the energy will be reduced, and therefore the amplitude of the waves is decreased. Okay, I mentioned on Monday that energy of the wave has something to do with the amplitude of the wave. The bigger your amplitude, the higher the wave is, the bigger the energy. Think of tsunami. Okay, tsunami has a very high amplitude, okay, and so it's very high energy. So when it hits the city, boom, okay, all will be gone. Okay, so diffraction of water waves produces a calm water region suitable for docking of ships, okay, and water recreational activities. So you want to have this kind of gap over here that is done by these two barriers, so that when a wave comes in over here, it will be much calmer, as opposed to kalau dia berada di sini. Okay, over here is much more stronger. Okay, and interestingly, the other day I was in KK and I went up to this Grandis Hotel, which is next to Surya Sabah, and I saw this same thing. Okay, I saw this same thing over here. So this is the view from the rooftop of Grandis Hotel, if you know where's Grandis Hotel. Okay, and I saw, hey, look, they built a barrier over here, okay, but they left a gap. Okay, and at first I thought, oh, okay, I guess the gap is for all these construction ships to come in. They're building something over here. Okay, but I realized that there is a function to this gap as well. Okay, and the function of the gap is, in case it gets very rainy, very stormy, and the waves get very high, when the waves pass through here, okay, when the waves pass through here, okay, it's going to be diffracted. Okay, it's going to be spread out. Okay, because the waves are coming in like this like that. When it passes through this gap, most of it is going to be blocked by this barrier. But the one that passes through here is going to be diffracted. And generally in here is a lot more calm lah. Obviously, you want it to be more calm lah, because you're bringing in construction stuff. You know, you're bringing construction stuff to, you know, for building lah. So you don't want all the cement to fall over and everything, right? So you want, you know, a much this one. If you have a chance, okay, you can go to Surya Sabah. I think if you go to Surya Sabah, like all the way to the top floor, you can see this also. But I saw this at the Grandis Hotel lah. Okay, the swimming pool at the Grandis Hotel, which is on the rooftop, you can see this. Okay, and so if you go there and see this, then hey, okay, yeah, this is diffraction. Ada juga Cikgu Markus cakap pasal ni. Okay, sorry, just quickly moving on. So audio frequency generator connected to a speaker placed near the wall. 3 students ABC standing around the corner. The generator and the speakers can produce sound at the same speed but with different frequency. Now, when a higher frequency is generated, only student C can hear the sound clearly. When a low frequency is generated, all 3 students can hear the sound clearly. Okay, so why is this happening? I'm going to quickly go through this. So you take a screenshot of this, and then after that you copy this later. Okay, now frequency is inversely proportional to wavelength. Means that if the frequency is big, the wavelength is small. Okay, so high frequency, small wavelength. So C only can hear. Okay, so it is difficult to diffract. That's why only C can hear clearly. But if you have a low frequency, the wavelength is longer. Remember, diffraction is better when the wavelength is bigger. Okay, wavelength is bigger because frequency is smaller. It's all connected. Okay, so sound is easily diffracted when there is a long wavelength. So all 3 students can hear this sound, okay, very clearly. Even though this A is standing very far away from the speaker, okay, he can actually hear. Because when you change the frequency, okay, the wavelength is much longer. Okay, these are owls. Okay, owls are able to communicate across long distances in the forest because they are long wavelength hoots. Okay, they're hoot, hoot, hoot. Okay, very long wavelength. Okay, so you can hear an owl from very far away. Okay, because the sound of the owls will diffract through the space between the trees in the forest. The trees in the forest, if you think about it, okay, this owl is getting very annoying. Okay, the trees in the forest act as slits. And they act as slits. So this one tree, and they act as slits. And remember this sound wave. Sound wave has a very, very big wavelength. Okay, so it's very easy for sound to diffract. Okay, and that's why, because it is diffract, yes, you will hear it softer because all the energy is being spread around, but you can hear it. Okay, you can hear it from very far. Okay, because of the diffraction of the hoot. Okay, another one is, okay, elephant. Okay, so infrasonic waves, waves are also a type of sound waves that are produced by elephants, have long wavelength, okay, to facilitate long distance communication between elephants. Let's not go to ultrasonic. Dolphins, whales, all those are ultrasonic. Let's talk about infrasonic first. Okay, so again, sound waves. Okay, so we always think that it's because they are toot, very loud, right? That's why they can hear. But actually, it's not just that. No, they can hear from very far away. Okay, and that helps elephants to communicate with one another. Believe it or not. Okay, one last one. Credit card. So diffraction of light waves can produce holograms, which are used as safety features on bank cards, such as debit cards or credit cards. Okay, and and this is actually found on even in your IC. You know, your IC, there's a hologram inside your IC, right? Like if you turn off the light, if you just on the ultraviolet, right, you can see a picture of yourself. I'm not going to show you my IC in public lah, okay? But you can take out your IC, you can watch it yourself. Your bank card, if you have a bank card, you see this hologram over here. Okay, those are safety features lah. Okay, that can be this one. So the diffraction of light waves can produce holograms, which are used as, it's the same thing lah. Okay, which are used as safety features on this one. Okay, and that's why there is a picture inside that hologram at certain angles. okay, where the light hits this one, okay, you can actually see the hologram, the picture inside the hologram itself. Okay, our IC is an excellent example of this, as I said just now. Credit cards, bank cards, they also use this technology. Okay, and it is used as a safety feature because it's not easy to produce holograms. Okay, so that's why some, you know, if let's say you have a fake card, okay, it's very difficult to produce holograms because apparently there's this like special machine that can only do it, and it's not that cheap. Okay, so appreciate your IC because your IC is quite high technology. How much do you pay for it? Not much. Okay, all right. So for this Friday, what I would like you to do, we're done with this subtopic now, by the way. For this Friday, I would like you to answer question number 4 and 5 in your tutorial. Only number 4 and 5. Please don't answer question number 3. Okay, question number 3, there is something wrong over there. So please answer question number 4 and number 5, and we will do a discussion of this on Friday. All right?